Hello, this is the presentation on colligative properties of solutions, section 15.3, and also heterogeneous mixtures, section 15.4. Start off with a trivia question, just like the questions before. You need to figure out what these stand for. If you want to pause the video right now, you can take a look at them and try to figure them out. Colligative properties. What colligative properties are? They are properties that depend on the number of solute particles and not what those particles are. We're going to get to what the actual properties are in the next slide, but let's take a closer look at the number of solute particles. So a solute, again, is something that's dissolved in a solvent. For example, when we made our Kool-Aid, the solute would be the sugar. If you make some salt water up, some sodium chloride in water, sodium and the chloride ions are the particles. So if you have sugar, sugar does not dissociate. It is a molecular compound, molecule made up of atoms that are non-metals, just carbon, hydrogen, and oxygen. So those do not break apart into ions or anything. They stay as one big unit. And so a glucose molecule is just one particle. If you have something like sodium chloride, that's an ionic compound. It is a metal bonded to a nonmetal, and when that one dissociates in water, it dissolves in water, it'll separate into its two ions, Na plus and Cl minus. So that one has two particles. If you have something like magnesium chloride, that one's going to have three particles. You'll have one magnesium, 2 plus charge, and you'll have two chloride ions. And so you'll end up with three particles. So the more particles you have, the greater effect on these colligative properties. Let's take a look at the colligative properties that we're talking about. The first one is vapor pressure lowering. Remember, vapor pressure is if you have some sort of a closed container and you have a solution in there, you will get some of that solution vaporizing and you will get the gas particles in that area up above it, and those gas particles are moving around. They're banging against the sides of the container, causing pressure, and that's what vapor pressure is. When you have particles that are inside here, you have things that are dissolved in here, that's going to lower that vapor pressure, so you'll have less particles in this area up here. You'll have less particles there. And that's because, remember, when something dissolves, water totally surrounds those particles. And so that's what's going to happen. You're going to have a lot of the water that's bound up, totally surrounding those particles, so they can't vaporize. A lot of that water can't vaporize because it's surrounding those particles. That's why the vapor pressure is lower. Our next one, boiling point elevation. It's going to, if you add particles to it, it's going to increase the boiling point. Temperature is going to be greater. The boiling point is going to be greater. Same exact rule for this, but here you're going to have an open container. You're going to have these water molecules that are bound up with that solute, and so you'll have less water that's able to boil off at a particular given temperature. Freezing point depression. You will lower the freezing point if you add particles to something. So you add salt in the winter to the roads to melt the ice, and that's what happens here. You get those particles. It will prevent the ice from crystallizing out. And so you add the sodium chloride. Typically, is what's used. So it'll lower that freezing point. So if you have temperatures in the 20s, in the teens, add a bunch of salt to the ice that's frozen because it's below 32. You'll lower that temperature, that freezing point, to below that temperature, and the ice will melt. If you had something like calcium chloride is more effective because that will dissociate into three particles. 1 calcium, and 2 chloride. So that one's going to be more effective than sodium chloride, which is going to have 2 particles is all. The reason sodium chloride is typically used is because it's a lot less expensive. You can put a lot more sodium chloride on for the price compared to the calcium chloride. So here's a question for you. Which will lower the vapor pressure the most? And here are your 3 choices. Think about it for a minute. Decide what your answer is going to be. The whole key is to decide how many particles that particular compound is going to have. So let's take a look at this first one. Potassium iodide, that's an ionic compound. So that one's going to dissociate into 2 particles. You'll have the K and the I. Here's another one, C6H12O6. That is a molecule. So that one is not going to dissociate. It's just going to, actually it is going to dissociate. It's going to get into solution, but it's only going to have 1 particle. And that's it, because it is a molecule just made up of nonmetals. Carbon, hydrogen, and oxygen are all nonmetals. So it's not going to break apart into more particles. This last one, sodium sulfate, that one's going to dissociate into 3 particles. You're going to have 2 sodiums and 1 sulfate. And so that one's going to have 3 particles. So the correct answer is Na2SO4, because it will form 3 particles. Electrolytes, I think we've talked about these before. They throw this definition in here. Those are ionic compounds that dissociate in water to form a solution that conducts electricity. So sodium chloride. Ionic compounds are going to be your electrolytes. Sodium chloride, potassium nitrate, whatever. Because when you have that compound in water, it's going to form its ions. And those ions is what allows electricity to pass through that solution. So that was the end of 15.3. Now let's look at 15.4, heterogeneous mixtures. More trivia here. Again, if you want to stop the video, take a look at these, see if you can figure out what they are. So far up to this point, we've been covering the homogeneous mixtures, solutions, been talking about that the whole time. Now we're going to take a quick look at the heterogeneous mixtures. We're going to be looking at suspensions and colloids. Actually, we're going to be looking at all 3, comparing and contrasting the 3 types of mixtures. Let's take a look at suspensions. Suspensions are the largest particles. We're going to be looking at these 3 in comparison with their size first. Let's take a look at the particles of suspension. They're going to be large. They're going to be greater than 1,000 nanometers in size. Particles will also settle out. If you have the suspension, for example, dirt and water, the particles will settle out over time. They can also be filtered because the particles are so large. Colloids, the particles larger than solutions but smaller than suspensions, so they're going to be the middle size, the mid-size particles, greater than 1 nanometer, less than 1,000 nanometers. It's a good time to mention that suspensions will be less than 1 nanometer. Those are the small ones. That's what we've been covering before. They can't be separated. They're not going to exhibit some of the effects that we're looking at coming up here in a minute here, because their particles are so small. But colloids are the middle zone, greater than 1 nanometer, less than 1,000. They will not settle out like suspensions, and they cannot be filtered. So suspensions will settle out and can be filtered. Colloids will not settle out and cannot be filtered. If you look on page 477, I'd highly recommend you do this. You're going to be responsible for some of these colloids, knowing what they are. There's some examples of colloids using all the different phases, solids, liquids, and gases. You should definitely take a look at those and see what's there. Now we're going to be looking at a couple of different effects for suspensions and colloid. The first one is the Tyndall effect. That is the effect seen as a heterogeneous particle scatters light. So it's only going to be on colloids and suspensions. Solutions do not exhibit the Tyndall effect. A couple of examples of the Tyndall effect is if you have a foggy night and you see a car driving by, you can see its headlights reflecting the fog. That is the Tyndall effect. Also, if you have smoke in a room, here's an example. You have smoke in the room and you have the sunlight coming in the window here. You can see this hazy area right there. That is the Tyndall effect, where the light is bouncing off those particles, those smoke particles, and scattering the light. So that's the Tyndall effect. Last one is Brownian motion. Brownian motion is the movements of these colloidal particles, the particles that are dissolved in that material when they collide with solvent particles. So remember, the solvent is like the water, for example. So whatever you have dissolved in there is being hit by the solvent particles. This will help prevent settling when you're talking about colloids. Help it so they don't settle out with all this. Keep on hitting it from all sides, bouncing it around, keeping it in suspension so it doesn't settle out. It can be seen under a microscope. If you take a look at this colloid under a microscope, and if you have the correct light shining on it, you will see little flashes of light because these solvent particles are hitting hitting these other particles in there, hitting the colloids, and bouncing, reflecting the light, and every now and again it'll bounce the light back through the microscope so you can see the little flash of light. So the Brownian motion is just going to be for these colloids. And that concludes our presentation. Hope you enjoyed it.